We have come to the end. This is going to be the graph of the last parent function of the year for us. And it's a fun one. We're going to graph arcsine of x. And a quick reminder, arcsine is just another name for the inverse sine of x. I prefer the name arcsine as opposed to inverse sine because I frankly hate this little negative one right there. It looks like an exponent, and students read it as an exponent, but it's not an exponent. So I say, let's just pretend that we don't know what that is. I'm going to draw a quick picture to remind you of the idea of an of inverse functions in general. So when you take a sine function, what you're doing is you are taking an angle, plugging it into some magic box we call the sine, and out comes some decimal. It's really a fraction. It's a ratio between 0 and 1, I guess between -1 and 1, the ratio of the opposite of the hypotenuse, etc. Great. We usually see it as a decimal because it's irrational. The idea of the arcsine is to do that in reverse. It's to take the decimal and plug it into the arcsine. So the output from the sine becomes the input into the arcsine, and the result is the angle that we started with. So into the arcsine we put a decimal, the answer from a sine, and out we get an angle. Well, in order to think about what numbers could go into arcsine, we need to think about what numbers could come out of sine, and I wrote it there. They are decimals. Has to be a decimal, only numbers between -1 and 1. Right? There's no time you'll ever get a 2 to come out here. It'll never happen. So you're never going to be able to put a 2 into the arcsine. Okay. In order to take a look at what the graph looks like, let's plot, do what we always do. We'll plot some easy points and then see if we can see the pattern. So we'll make a table of values to see what f of x equals arcsine of x looks like. In order to do that, we're going to start with sine, because those we know already. We know a bunch of values for sine. We know the sine of 0 is 0. We know the sine of pi over 4. We know it is root 2 over 2, which we could certainly keep writing it as root 2 over 2 if we want. It's also about 0.7 or so. And the sine of pi over 2, we know that's 1. We know the sine of 3 pi over 2 is -1. We know that the sine of pi is 0. A bunch of things that we know. I'm not sure why I went out of order there. Okay, so let's do some inverses here. And the idea, remember the idea behind an inverse function is we can just switch the x and y column to go from a function to its inverse. Notice how what I did also with the variables here, I switched the variables. Here, the input into sine was theta, because that's the symbol we often use for angles. But I would never do arcsine of theta, because the number we put into arcsine is not an angle. So this x value should never be an angle going into arcsine. It should always be some decimal, or number between -1 and 1. Okay, so I know that if I switch my columns, I'll still have 0, 0. So arcsine will still go through the point 0, 0. If the sine of pi over 4 is 0.7, that means the arcsine of 0.7, which remember is root 2 over 2, but that's kind of annoying to put onto an x-axis, is pi over 4. And the arcsine of 1 would be pi over 2. So we can graph those points and see how it starts. What I'll do here is I'll just make this be 1. Nope, too far. That's -1, and that's 1. So 0.7 is a little bit more than halfway, almost 3/4 of the way. And I need to scale my y-axis, and you can see that these numbers up here are in terms of pi. So I'm going to scale my y-axis in terms of pi also. Let's do this as pi over 2, pi. So the arcsine of 0.7 is pi over 4. So 0.7, pi over 4, that's right about there. The 0.7 is a little bit hard to place precisely, but that's okay. The arc7 of 0 is 0. About that one. Arcsine of 1 is pi over 2. So it's a little bit hard to tell, but notice how that, it looks almost like a straight line, but it's not quite a straight line because it really is not increasing evenly. It really is increasing at a bit of a curve. Okay, but we can do more than this. I'm gonna put a hold on these guys for just a minute. We know some other values too. If we want to get some different values for our arcsine here, we can think about the sign of numbers that are a little bit less than 0, so like negative pi over 4. We know that that sign of that would be negative 0.7. So the arcsine of negative 0.7 would be negative pi over 4. And what you'll see by doing this is if you just plot that point here, that got a little bit too big. If you plot that point here, and then plot the next one, negative 1, well here, the sign of negative pi over 2 is negative 1, and so the arcsine of negative 1 is negative pi over 2, but right now, if you haven't already caught it, you might see the problem that I'm going to come up with. I just said that the arcsine of negative 1 is negative pi over 2, right? I took this line and I turned it into that. But you might be looking at me and saying, wait a minute. Why didn't we use that row and say that the arcsine of negative 1 is 3 pi over 2? So I would go up here. Why can't I do that? And you might have caught this problem already before where I said that the arcsine of 0 is 0. Let me undo some of those highlighting so it's not so confusing. The arcsine of 0 is 0. I said that because I took this point and I just switched the x and y, but why didn't I do that point? Why didn't I put a pi here? Say the arcsine of 0 is pi. And the angle that makes, or the sine of, let's go 3 pi over 4 is 0.7, or root 2 over 2. So why didn't I say that the arcsine of 0.7 was 3 pi over 4? Well, why doesn't this work? The arcsine of 0.7 couldn't also be 3 pi over 4? In which case I'd have a graph that looks like this. And it actually keeps going like this. And we know that sine keeps going side to side, so shouldn't arcsine keep going just like that? And here's my problem. That's just not a function. The reason why arcsine can't look like that is because then arcsine wouldn't be a function. And we want arcsine to be a function. So even though, yes, it is true, when you say arcsine, you're saying the angle whose sine is x. And so if you say, hey, what angle has a sine of 0, there is an infinite number of answers to that question. Angle whose sines are 0. It'll keep happening over and over again. But in order to make it so that we have a function, I need to only be able to answer that once. And so we don't include any of these other points. And we just leave it at that. And so what we do is the word for this is we restrict the domain, the range. The domain we already said before is everything that comes out of sine can go into arcsine, so it's everything between negative 1 and 1. But the range is a little bit trickier. We have to stop the range from running out of control, otherwise it would not, our curve would not be a function. Our equation, our function would not be a function. So arcsine would not be a function. So what we do is we restrict the range. We say the only answers I'm willing to get out of arcsine are answers between negative pi over 2 and positive pi over 2. Even though, sure, there are answers in the second and third quadrants that would also work, we ignore them. I'll just show you on Desmos how this works. So if I take y equals sine of x, we know that already. If I switch the x and the y, Desmos will graph this for me. It's cool that Desmos can do this. That is x equals sine of y. If I kind of zoom in here, you can see that it just repeats itself because, there are a lot of different ways that sine could equal 1, which means there would be a lot of different x values you would get. Sorry, a lot of different y values you would get if you plug in, the x value of 1 here. That was the problem we had before that makes it not a function. And so what we do to fix this problem is when we use arcsine of x, it is automatically restricted to just this area in here. If I turn this guy off, you can see arcsine of x is just restricted to just the area between negative pi over 2 on the y value and